Now, so therefore, what is that, right? Therefore, what we have is the index of reflection depend on the wavelength too. You got it? Hello? That's why we see this phenomenon. When the white light going into a prism, and when they emerge out from the other side, and instead of you see the white light, you see a spectrum on it. Good? Hello?
Yes, got it. And
the violet travel longer than the red. So therefore the violet bend more. Now then this thing is called prism, right? So one thing I know that this prism look like an equilateral, right? So in other words, everywhere is 60 degrees. Right, am I right? Hello?
Yes.
Now if this is 60 degrees, right? So therefore, now by the way, what is this angle equal to? This angle will be equal to what? This angle will be equal to 90 degrees minus theta 2, right? Am I right? The reason is that here is the normal line, right? Am I right? Hello?
Yes.
Now, so therefore, equal to what? That angle will be equal to what? 90 minus 32.8 degrees. So will be equal to what? 90 minus 32.8, 57.2, right? So 57.2. Now then what is this angle equal to? Now we should be able to calculate that, right? Now let's say I'm gonna call this angle to alpha, right? So one thing I know is 60 plus 57.2 plus alpha equal to 180, right? Am I right? Hello? Hello?
Yes. Yes.
So therefore, what is alpha equal to? So alpha will be equal to 180. So I have 180 minus 57.2 minus 60, right? So it will be 62.8, right? So then I know that again, I'm gonna use the argument of the angle here, right? This is right angle, right? Am I right? Hello?
Yes.
So therefore I know that theta alpha plus theta phi equal to 90 degrees, right? Am I right?
Yes.
So therefore, what is theta phi equal to? So theta phi will be equal to 90 degrees minus 62.8. So will be 27.2. Good. Now with this in mind, then I should be able to find the theta 4, right? So what is theta 4 equal to? So I write that, right? Theta 4 will be, so like I said, I already write it upstairs, right here. So theta 4 will be equal to arc sine 1.662 times sine 27.2 degrees divided by 1. So what is this? So I'm going to take a sine multiplied by 1.662 equal, and then take an arc sine 49.4 degrees. 0.3 degree. Good? Hello? Hello?
Yes.
Now you should be able to do the purples, right? The way you do the purples is you substitute the different value, right? Hello? So that will, instead of here will be n, that will be n purples, right? And so forth. Make sense? Hello?
Yes.
I just follow what I'm doing, right? But make sure that you substitute the right index of reflection for the purple light. Are you with me?
Yes.
Now, what I'm gonna do, I am going to, right? The way you do this problem, you need to find this length, right? Now, let's say that I'm gonna draw that again. You need to find this length. You understand what I'm saying? Hello?
Yes.
Now, if I look at the way I draw, right, then how many times the light beam reflect from the left side? 3 times, right? Am I right? Hello?
Yes.
Now, but that's not what we guess, right? We have to do that, right? Now, what is this link equal to? Now, one thing I know that is I can draw a line here, the normal line, right? So what I know that is, what is this link, right? Let's say this link is D. Am I right? Hello? Hello?
Yep.
Now, one thing I know that is, what is that? Now, I'm going to write it quick, right? D divided by 2 divided by S equal to tangent 24.8 degrees. Do you agree with me? Now, why I'm doing that? I'm going to draw a better line here. Oops. Now I'm going to draw a normal line here, right? So use different color. So this angle is also 24.8 degrees. Am I right? Hello?
Yes.
And then D over 2 divided by S will be tangent 24.8, right? Hello?
Yes.
Now then I'm going to calculate what is that D equal to, right? So D will be equal to D over 2 will be equal to S times tangent 24.8 degrees. So what is D equal to? D will be 2S tangent 24.8 degrees. So will be equal to what? 2 times 0.65 tangent 24.8. So what is this? So 0.65 times 2 times 24.8 tangent, that will be 0.6. Hello? Hello? You got it?
Yes.
Now, if he has 0.6, right, that will be the same thing here, right? That will be a 0.6. Right, am I right? Hello? Hello?
Yes.
Now, then I know that it's always, then here will be 0.6, right? But if that's 3 times, then the total length here will be what? Am I right? Hello?
Yes.
Then we know that my original length of the mirror is 1.3, right? So the most you can reflect that is what? How many times? Right? Am I right? Hello?
Yes.
Well, therefore, the maximum time way you can reflecting back on the left mirror will be 2 times. Right, that will be the question. Now, let me see what else they asked. They asked on the right side, right? The right side, I have 1, 2, right? Hello? So now it's for the left side. Then the question is, what is the right side? Then you look at that right here, right? 1, 2, right? What is the length here? So if you find the length here, 0.6, 0.6, here will be at the midpoint here, right? What is this length here equal to? Hello? Hello? So it will be 0.6, 0.6, right? Am I right? Hello?
Yes.
And that will be 1.5, right? So 1.5 beyond the length of the mirror, right? So again, how many times you can reflect? Again, well, how many times?
2 times.
2.
2 times, right? What is, I hear a male's voice. What is that, John?
Yes, sir.
Yeah, usually you're very quiet, right?
Sorry about that. Just writing notes.
There's nothing you can write. I mean, you know that I write it, I put it online, right? You know that?
Yeah,
Did you
but I
read
get
my...
extra practice.
Okay, all right. Now, let me see what else I'm gonna do. Now I'm gonna do one more at 21. Now keep it in mind, right? Your number will be different than my number. So your here may not be a 0.65, right? Okay. Now I'm gonna do 21. Now 21 look like this. Now 21 we have a 45, 45, 90. So each of this angle is 45 degrees. Now then, what is this? As show the light beam that enter the prism at the midpoint of the long side parallel to the base exit the prism at an angle 20 degrees below the horizontal. So given here is 20 degrees. Are you with me? Hello? Hello?
Yes.
Now, what we try to find that is we want to find the index of reflection, right, of this prism. Now, I'm going to draw this. Okay. Let me pause it a little bit. Hello? Sine A plus B, right? Sine A minus B, right? What is that equal to? Anyone remember that? No, you can go find it and tell me. Hello? The sum of the sine, right? Okay, go search it and tell me right now. How about that? Hello? Sine A minus B, right? Hello? Okay, no one tell me. Now, you should remember that, right? Sine A plus B, right, will be sine A cosine B. Sine is just follow the sine, right? Plus and minus cosine A sine B, right? If you have cosine A plus B, then you have cosine A, cosine B, and then the sine will reverse, right? Minus sine A sine B. Are you with me?
Yes.
Yes. So therefore, what does this look like? So I have A minus B, right? So I can write this as N sine alpha cosine 45 minus cosine alpha sine 45 equal to sine 20 degrees. Good? Good? Hello?
Yes.
Now then, the rest of them, you should be able to solve it, right? You can, I mean, you just do this and you should be able to solve it. You got it? Just solve for the N, right? All right. And lens is for refractions. Now we have different type of mirror, right? Or lens. Now I'm gonna talk about the mirror first. You have a plane mirror. Now plane mirror has nothing else, right? So when you have a light coming in, and then they're gonna reflect. Well, let's say I have a candle here. So what happened is you're gonna see a candle on the other side, right? Am I right? And here, so I can call the DO, right here will be DI, right? Am I right? Hello? Hello?
Yes, right. Yes.
The angle of, I mean, there's nothing special, right, for the plane mirror. The DI is equal to DO. So why we see the image like that? Well, you can think about that. The light, now let's say I have an eyes here. Now you look at the light, when the light reflects. I'm going to use the red color to trade the path. Now I should use the solid line. The dashed line means the virtual path. The same thing here. Right, that's why it look like the image in the back, right? So this type of image, they are virtual. For the mirror, if the image is in the opposite side, of object, are they in the opposite side? Hello? Are they in the opposite side, right? The image and the mirror, the object in the opposite side of the mirror, right? Is that right?
Yes.
So therefore they are virtual, right? For mirror, it's always like that. Now, then I can tell that the image is virtual, and what else I can say about the image? Then when you do the characteristic of the image, right, you need to tell me the three things. We were virtual, right? Well, real or virtual? Now, obviously here is virtual, right? Hello?
Yes, it's virtual.
And then you need to tell me the size, right? Enlarge or diminish. Now you have the same, enlarge. Enlarge mean they are bigger, right? Or diminish. So which one? They are same, right? Hello?
Yes.
Hello? And then what else you can tell? They are erected. Erected mean they're same orientation or inverted. So what is this? They are erected, right? Hello?
Yes, they are.
Now, then this mirror, no interest, right? They are plain mirror. It's just like that in the bathroom and you look at the mirror in cell, right? You just look like that you're inside the mirror and the same distance from your distance to the mirror distance. Now, what we are talking about here is we are talking about the different type mirror, right? We call them a concave or convex mirror. Now, think about it, I have a sphere. Now, let's say I have a sphere, right? Now, I'm gonna cut a piece of them out, right? So that will become like this, right? Hello? Hello?
Yes.
Now, depend on what side I am coating my mirror, right? So if I'm coating in the outer side, or I'm coating the inner side, then I have different mirror, right? So if you're coating on the outer side, right, then I will have a convergent mirror. If I'm coating the inner side, then I have a divergent mirrors. Now, then the name is also different, right? Now, if you're coating an outer side, we call them a concave mirror. Here will be a convex mirror, okay? The meaning is the same, right? Hello?
Yes.
Yes. Now, why we call them a convergent mirror, right? Now, for this type of mirror, now each of the mirror they have, now this type of mirror we call it spherical mirror. Why it's called spherical? Because they are a piece of a sphere. Am I right? You're cutting a piece of sphere out, right? So we call them a spherical mirror. Now, and I know that for a sphere, I have something we call what? Hello? What does R stand for?
Radius.
The radius, right? Now, for this type mirror, right? Now, why we call them convergent mirror, right? So I'm gonna redraw this here. Now, there's different way we can redraw that, right? So the simple way is just draw this. Now, for this type mirror, right? You always bisect in the middle, right? I'm gonna draw a line here. Okay, let me draw the line. Now, this line, we call them a principal axis. Okay, that's just the line that bisects the mirror. Now, remember that this mirror corresponding to a radius, right? Hello? Hello? Why they have a radius? Can anyone tell me that why this mirror have a radius? Why this mirror have a radius? Can anyone tell me that? Remember that how we get this piece, how we get this mirror? We are cutting a piece out of a sphere, right? Hello?
Yes.
So therefore, this radius is the radius of the original sphere. Now, this length, we call them a radius of curvature, right? So R will stand for radius of curvature. Now, and for the spherical mirror, right, if you bisect the radius of curvature, then you will get a focal point. So therefore, what's the relation between the F and R? F is equal to R divided by 2. And we call the focal point of the spherical mirror. Hello, are you there?
Yes.
Now, why we call them a convergent mirror, a concave mirror, right? Remember that either convergent or concave mirror, right? The reason for that is if you have a parallel line in, let's say I'm gonna send in a parallel line in, right? The light. Then what happened? Then the light will convert to a focal point. I'm gonna use the dashed line to represent the reflecting light. Good. Hello. Hello.
Yes, good.
Now, another way, for the divergent mirror, right? Divergent mirror, same thing, right? So I'm gonna draw this. Now, where you see the convergent mirror, right? If you have this Olympic game, right? You see that every 4 years they collect the fire under the sun, right? Do you know what I'm talking about? Hello? Now, one thing I know that for the concave lens, right? The F is always positive. We always use the F in here. For the convex lens, right, we're gonna use the F in the other side, so therefore F is negative. Now let me tell you why we call them a divergent mirror, right? Now let's say that I have a parallel line coming in. Hello? Now this line will diverge, right? This line we're gonna go this way, right? Am I right? Hello?
Yes.
Now then, how they diverge, right? Diverge, they look like this line is coming out from the focal point on the other side. So look like that this line is coming out from here. Good. Hello? Are you with me?
Yes.
Now I'm gonna do some example here, right? Now let's do the concave mirror first. So what I'm trying to tell you in the following is graphical method. Graphing to locate the image. It's all about the image, right? Now I'm gonna do case by case, right? So I'm gonna do the concave mirror first. Now I have to draw a principal axis, right? Now then I'm gonna define my focal point, right? Now sometimes they don't call R, they just say C, but it was really a center, right? Am I right? Hello?
Yes.
You can write this C and F, right? And the relation is F is equal to C divided by 2, or R divided by 2. Now, the way your graphical method to form the image is depend. Now, you can think about it, right? Now, I can put my image. So where can I put my, no, I'm sorry, the object, right? I can put it behind the C, right? What else I can put it at C, right? Am I right? Hello?
Yes.
And between C and F, right? And then what? At F, right? Hello? Or in front of, that will be less than the F, right? Or you can say that between F and the vertex, right? Am I right?
Yes.
Now, each of them, the image have different behavior, right? Now, let me do one. Now, it's just no time to do all of them, right? You should practice like what I'm doing. Now, let me draw the better. Now, I'm gonna put my image behind the C. Yeah, like that. Hello. Now, the way you're gonna find the now I should say that I put my object behind the C, right? I want to find the location of the image. Now, then remember that I have a parallel line coming in, and they're gonna what? They're gonna falling on the focal point, right? Am I right? Hello?
Yes.
But it will not tell me where's the location of the image, right? And then we need a couple more drawings. Now, let me zoom it in, right? Now, another way you draw that is, then when you have a light, the image, the way coming in from the top of the object hit the vertex. Now it should be solid light, the incident light, right? And then they're gonna reflecting back in the same way. Now let me measure this angle here, right? So this ruler, very good. What angle? Hello? Hello?
80 degrees.
80 degrees, right? So then when they are reflecting back from the vertex, they should be 80 degrees too. You got it? Hello? Now, so therefore, where's the location of an image, right? Now, keep it in mind, when you're doing all of this, the location of the image is always at the what? The intersection. The key word here, intersection. Where's the intersection? Can anyone tell me that? Hello? The intersection will be here, right? Am I right? Hello?
Yes.
Now then, what does the image look like? The image will be look like this, right? Now I'm gonna use the dashed line to represent the image, right? That will be my image. You got it? Now what can I tell about the image? They are real or virtual? Remember that for the mirror, if the image is in the same side of the object, they are real. If they are in the opposite side of the object, they will be a virtual. So real or virtual?
Real.
They are real, right? And then are they what should I say that? Are they bigger, smaller?
Smaller.
Smaller, right? Or diminish. Now then, are they erected or inverted?
Inverted.
Inverted, right? Good. Hello. Now we have a lot of case right here, right? So now let me draw one more case and I'll show you the equation here. Now I'm gonna do another one here. So remember that I have 5 cases, right? 1, 2, 3, 4, 5, right? They all have different outcome. Now I'm going to draw, let me do this. Then I'm going to use the ruler here. Now I'm gonna define my F and my C. Now what I'm gonna do, I'm gonna put my image between the F and the vertex, right? Hello? Not the image, keep saying the image, the object, right? Good? Hello?
Yes,
Yes.
good.
Now what I'm gonna do, so I have parallel line coming in, right? Use different color. And then they're gonna falling on the focal point. So we'll be here. Now remember the key is find the intersection of the reflecting wave, right? Good. Now what else I can do? Well, I said that if you have, now I'm gonna zoom in. Now then I have the light hitting the vertex, right? Now what is the angle here? Keep it in mind. What is that?
25.
All right. So the light hitting the vertex. And then they're gonna reflecting out, right? 25, right? You like my drawing board, right? Do you like it? Hello?
Yeah. Yes.
I don't think you will find any instructor doing like me, okay? If you find one, let me know that. Okay, see here. Now the arrow will show you the direction of the incident way and the reflecting way too. I'm gonna put it clear. You got it? Hello?
Yes.
Now that's you have another way to draw that, right? Now what is another way to draw that? Right? I did not show you in the last example. Another way to draw that is if you have a light going through the center of curvature and hit part of the object, right? Now the only way you can hit that is the tips of the object, right? Am I right? Hello? Hello?
Yes.
So you can think about that way. Now, if you have a light coming in from the tips of the object, they are aligned with the center of curvature. They will reflect things straight back. You understand? So in other words, this point here act like a plane mirror. Hello?
Yeah.
It's because why it's plane mirror. Remember that if this point is really a tangent line, right? This point is really the tangent. Am I right? 90 degree here, right? Hello?
Yes.
Yes.
Okay, I'm gonna erase this. Oops. Okay, so keep it like this. Now, one thing you see all this, the green, the red, and the blue, they never form an intersection, right? Am I right?
Yeah.
Yeah.
Now, then what happened? Look, they never, the way you see the slope of the line, they never form an intersection on the left side. The only way you want to find an intersection is you're gonna extend that line to the right side. Now I'm gonna zoom out. I look like the image is very big. Are you with me?
Yes. Yes.
Yes. Did you have you learned this in high school? Hello? Have you learned this in high school? No one answered. Okay. Do you know what I'm doing? Hello?
Yes, you're finding the intersection on the right side now.
Yeah, very smart today. Now, the way I'm drawing it is not very good, right? Now, if you draw better, you are all in scale, right? You should be able to find the intersection. You got it? Now, if I draw very bad, right, all these three lines, they will converge in one point. So in other words, where's my location of my image? So it will be here. You good? Hello?
Yes.
Now, what can we tell about this image? Now, I'm gonna characterize that, right? Characterize. So this image, we were virtual. Virtual, right? Because see, they're the opposite side of the objects. And this image is enlarged or diminished. Enlarged. And this image is erected or inverted. Erected, right? So, now you know what I'm saying, right? So you can draw all of this, right? Now, but That's another way to find the location of image, right? We call them Miller equations. We can verify that. Now, what does the Miller equation say that? Miller equation said that 1 over f. Now, by the way, I did not tell you that, right? Now, here will be my object distance, DO. And here will be my inmate distance, DI. You got it? Hello? Hello?
Yes.
Yes.
Let me ask you, have you seen that before in the high school? No, yes or no? Just say yes or no. I know one say yes or no. Yes? Hello?
No.
Okay, it's fine. Now we have this so-called Miller equation, right? The inverse of the f, the reciprocal of f is equal to the reciprocal of the object distance plus the reciprocal of the image distance. Now let's go and verify that, right? Now let's say that, now I'm gonna use this as example, right? Now let's say my object distance here is, what does that look like? Now okay, we should define the f first, right? Let's say f is, what it is? Let's say f is 10 centimeter. Good, hello? Hello?
Yes.
Now, what does my object distance look like, right? We can guess. The object distance, now I can use a ruler to measure that. I'm gonna zoom in. Now, if I call, now I'm gonna mark, oops, no, we cannot do that if you're mirror here. Now I'm gonna mark this a dot, so it's easy for us to measure. Well, we just need to go get an approximate number, right? Okay, you can say that 1, 2, 3. Okay, I have 1, 2, 3, 4, 5. Okay, 10. So I would say that will be 27 or 26, right? Good. Make sense? Hello?
Yes. Yes, it does.
Now, then I can calculate my inmate distance. Right? So what is 1 over di equal to? 1 over di will be equal to 1 over f minus 1 over do. Now, so therefore equal to what? 1 over 10 minus 1 over 20. Am I right? 26, right? I'm sorry. 26. So what it is, that will be look like 260, right? And 26 minus 10, right? Am I right? Hello?
Yes.
Will be 16 divided by 260, right? But remember that that's a reciprocal, right? I have to flip it over. Am I right? Hello? So it will be 16.25 centimeters. Now, my question is this distance look like 16.25? Yes or no? Yes, right? Hello?
Yes.
Right? Because see, the F distance is 10, the C distance is 20. The image is between 10 and 20, but it look like it's 16.25, right? Am I right?
Yes.
Now, then I can do this problem here too, right? The second one. I'm gonna use the blue color. I'm doing this one. Now, what does that look like? Okay, now this is my image distance, right? Now, what is the F, right? F is still 10, right? Hello? Hello?
Yes.
Now, what does DO look like, right? We can approximate that, right? It really doesn't matter, right? As long as they are less than F. Now, but I'm gonna use the ruler to measure that. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this look like, I would say the 7, right? Hello? Hello?
Yeah.
Approximately, right? Now, then I'm going to calculate the inmate distance, right? Am I right? Hello? 7 minus, is it right? Hello? Are you there?
Yes.
7 divided by 3. So what is 70 divided by 3, right? So I'm going to write it better. So 70 divided by 3, right, will be 23, negative 23.3. Now, my question is this distance look like 23.3? Yes or no? Yes, right? Hello?
Yes.
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 Now, then the question is how are we going to interpret this side, right? So the negative side tell me that I have a image in the opposite side of the objects. All right, so negative. Good? Hello?
Yes, good.
Now, that's another thing I want to tell you that, right? And now, what it is? Now, we have another quantity here we call magnification. What is magnification, right? We use a simple M, right? Magnification is really the, we call them an inmate distance divided by the inmate side divided by the object side, right? Okay, so magnification is equal to negative inmate distance divided by the object distance. Or you can write the inmate side divided by the object size. The height, I should say that. You got it? Hello? Now, what the magnification tell me that if M is bigger than 1, then I have enlarged. If M is less than 1, then I have smaller size. Now, if M is equal to 1, what happens? Can anyone tell me that? If M equal to 1 is what?
The same.
The same, right? The object and the image will be the same size. And what situation the M is equal to 1?
The plane mirror.
The plane mirror, right? You're very smart today, right? Now I'm going to find them. Now I'm going to do this as an example here. Hello? You see my cursor moving?
Yes.
Yes.
I'm going to use this as example. Now, what is my magnification for the second case? The inmate distance, right, which is 23.3 divided by the object distance, right? The object is, what is the object? 7, right? Am I right?
Yes.
Hello? Now, then, what is this? 23.3 divided by 7. Now, I forget to put a negative sign here. Remember that? I should put this way, right? Now I'm going to explain to you what does that mean. Am I right? Hello?
Yes.
23.3 divided by 7 is 3.3. So what does that mean? It means that the size of the image is about 3.33 times of the object, right? If you look at that, it's about same, right? The way I draw it is not in scale. That's why they are not exactly look like. Am I right? Hello?
Yes.
Hello? Now, what does that positive mean here? Now, if you look at carefully, I have a positive sign here, right? Positive sign mean what? They are in the same orientations. Same orientation mean what? The object is erected, the image always erected, right? That is the case, right? Am I right? Hello? Hello?
Yes.
Now let's say I want to find the size of the image, right? Let the object height is 3 centimeter. Am I right? Then I want to find the image height, right? So I'm gonna use the magnification, which is equal to HI over HO, right? Which is HI divided by phi. Am I right? Hello?
Yes.
Hello? So therefore, what is HI equal to? HI will be equal to times phi will be 9.99, right? Centimeter. Right, that makes sense, right? If you look at the picture here, they are about 3 times, right? Like I said, I did not draw very good, right? That's why they are not in scale. Approximately, the graphical method is say close to the result of the analytical method, right? Okay, hello? Now what I'm gonna do, I am going to, so I'm gonna draw the principal axis here. Now then I'm gonna define my focal point, right? Now let's do it precisely, right? 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5, 6. Now I'm gonna put here. Okay, 1, 2, 3, 4, 6. Good. Hello.
Yes, good.
Yes.
Okay, 1, 2, 3, 4, 5, 6. Right? That will be my the what is that? The center curvature, right? Now remember that we don't use it in the other side, right? We use the one in the other side. You will see that what I'm talking about. So we just use it as the reference to draw the focal point on the other side. So we'll be here. We'll be here, right? Am I right? The reason that they are diverse. Now what I'm gonna do, I'm gonna put an image. I'm gonna put an image on the anywhere. Now the convex mirror, very interesting property, right? I will tell you that one. They all form the virtual image. They all erected. They all diminish. So convex mirror, they form all the image is virtual. And then they are, what should I say then? They are all smaller. So I have this ruler here. That's why I cannot write it correctly. And what else? They all the same orientation of the object. Good. Hello?
Mm-hmm.
Always true, right? Now I'm gonna do a example here. Now I'm gonna put it between C and F. Now precisely, I'm gonna make it like for phi unit, right? Like this. Good. Hello? Hello?
Yes.
Now I'm going to, now we can do the calculation too. I remember 6 units. So my object distance is 6 plus phi, right? Let's say 9 centimeter. Okay, my F is 6 centimeters. Am I right? Now you have to bear with what? Okay, when you have a ruler, you're out of control sometimes. Now I'm gonna draw it first, and then I'm use the calculation to verify it. Now the light coming in, what happened when the where's the reflecting light? Hello? They diverge, right? It look like what? They look like they're coming out from the other side, the focal point, right? Am I right? Remember that I have a divergent mirror, right? The light is not converged. Hello? Right?
Yes.
Now then what happened? Now I did say that, right? Another way to draw that is if the light hitting the vertex, right? The vertex behave like a plane mirror. And then they're gonna reflecting out, right? Now let me zoom in, it's easy to see that. 19 degrees, right? Remember that? 19. Now I will need to extend it anyway, so I'm gonna extend it first. Now the light coming in and reflecting out, right? Am I right? Hello?
Yes.
Now you see that this line and this line never form an intersection. They are reflecting light wave, right? So I have to extend it to the other side, right? Where's the intersection? Hello? Where's the intersection? Here, right? Am I right?
Yes.
So
Yes.
therefore, what is the image look like? The image look like this. Right, now as I said that this image is virtual, right? Why is virtual? They are in the opposite side of the mirror. The object and image in the opposite side of the mirror. What else? They are smaller, right? Hello? Hello?
Yes.
Yes.
And they are, what else they are? They are erected, right? Same orientation, right? I should say that. Now then I'm gonna do my calculation here. Now, one thing I did not write right. Now, for the concave mirror, convex mirror, the F is always negative. You see why negative? I never use the focal point here. I'm using the focal point here, right? Am I right? Hello?
Yes.
Yes.
Now then I'm gonna calculate that, right? So I want to find the DI. Now I'm gonna jump the step. DI is equal to 1 over F minus 1 over DO. Am I right? Hello? But look at this equation here, right? Hello? Is that right? Hello?
Yes.
Yes.
Okay, what is that? 54. And then I have minus 9, minus 6, which is, what is this? Minus 15. But what is DI? So I have to flip it over, right? 54 divided by 15, right? So which is minus 3.6. Good? Hello?
Yes.
Now remember that my focal point, right? My focal point is 6 centimeters, right? So if this is a negative 3.6, Here is 6, right? Yes, right? Hello. Am I right?
Yes.
Now
Yes.
then I can do the magnification too, right? So what is the magnification? Now let's say my image side. What did I say about the image side? I think I was saying it's 3, right? So I'm gonna go back to measure that. I did say, okay, what is it? 1, 2, okay, it's 3, right? It's okay. So let's say the object height, right? Good. Hello.
Yes.
Now I'm gonna calculate that, right? Now remember the magnification is equal to negative DI over DO, but it's also equal to HI over HO. Now then I want to find the magnification, right? So negative divided by DO is 9. So what is this? So it will be 0.4. Now I have a positive sign here, right? What that positive sign mean? The positive sign mean that my object and my image, they are in the same orientation. Is it true?
Yes.
Right, they all pointing up, right? Now then, as it's the image is about 40% of the object. Hello? It's the image, the size of the image is 40% of the object. Is it right? Yes?
Yes.
Yeah, they diminish, right? Now then I can find what is the height of that, right? Now my HI is, HO is 3 centimeters. So therefore the image height is 1.2 centimeters. You got it? Good. Hello?
Yes.
Now you can go home and do this convex lens, right? Like I said, for the concave lens, I did 2. I did 2 out of the 5 situations. For the convex lens, and I can tell you that all the image is virtual, smaller, and erected. And you can do all the 5 situations, right? Behind the C, between the C and F, at C and F, and in front of the F. Are you with me? Hello?
Yes.
Yes.
Now, what I'm gonna do, I'm gonna give you a, okay, let me see whether we have. Okay, I'm gonna do the lens right now. Now let me see. Okay, I'm gonna pause it. Now, if you have the lens, they have 2 curvature, right? Form a lens, we call them what? We call them a convex meniscus. Now, what is the special about a convergent lens or the convex lens? The center part, right? If you look at the center part, right? They are thicker than the edge, right? Is that right?
Yeah.
Hello? Right? Now, then I have another type of lens, right? I have one side have a curvature, another side they are flat. Well, this type of lens, we call them a plano convex, right? Why plano? One side is flat, another side is convex, right? Hello? Now, then what is the next one? What's the name of the next one? Are you there?
Yes.
Yes.
What is the name of the next one? It's called a double convex. And why we call them a double convex? If you look at the curvature, right, they all same. Am I right?
Yes.
And they are, or in a simple word, you can say that they are symmetric, right? So they are symmetry, right? So we call them a double convex. They have the same center of curvature. Now, if you look at all the reading glass, right? all the reading glass will be a convergent lens. You understand what I'm saying?
Yes.
If you get O, you need a reading glass. They are all convergent lens. Now, in the same token, right? Now, then I have a concave lens, or we call it divergent lens. Now, what's special about a concave lens? If you look at all these three lenses, right? The center part is thinner than the edge, right? Is that right?
Yeah.
Now, then they have different name, right? We can, now they have two edge, they are different center of curvature. Then in this type of concave lens, we call them a concave meniscus. Or one side is flat, where another side is concave, then we call them a plano concave. Or both sides are symmetric, right? They have the same center of curvature. We call them double concave. Are you with me?
Yes.
Yes.
Now, what is the purpose of this lens? When did you see that? We use it all the time, right? Particularly now, right? All the handheld device or the computer or your smartphone, right? It's really destroy your eyes, right? When your eye destroy, what do you need? Hello?
The glasses.
A glasses? What type of glasses? What happened to your eyes? You have a near sight, right? Hello?
Yeah.
You know what is a near sight, right? Near sight means that you can see the close-up thing very clear. But when you take off your glass or whenever you don't have glass, you cannot see the further image very clear, right? Further object, right? Hello? Now we have something we call the power of the lens, right? Now what is the power of the lens? I'm going to show you this, or we call the diopter number. There's something to do with the optics, or now we call them a power of the lens, or it's called a diopter, right? Now, what is defined at? P is 1 over F. You got it? Hello? Now, let's say that, what is the common prescription, right? No one wants to tell me a prescription, right? Now, let's say that your power is -5. But if you go to buy a contact lens, you see the negative, right? Hello?
Yes.
Well, you don't want to tell me 5, right? Now, then I can tell what is the focal length of your contact lens, right? So what is F equal to? You got it?
Yes.
So will be your focal length will be, I believe that they are measured in meter. Negative. You got it? So, or you can write it in -20 centimeters. Remember, negative mean what? Negative mean they are convex, right? Negative mean is concave, I should say that. Or divergent lens. Positive mean what? Convex. They are convergent lens, right? Now, like your father, right? Your father need a reading glass, right? Am I right? Hello? Even myself, right? Hello? So for example, myself, my F is 1.5. No, my P is 1. So therefore, what is the glass I'm reading? F will be 1 over P. Positive, right? So I know it's convergent lens or convex lens. So it will be 0.67. That will be, what is that, 67 centimeters. Good, hello?
Yes, good.
Now, when you're doing the lens, now different, right? Now, when you're doing a lens, right? I'm gonna draw a lens. It could be a convergent lens or the convex lens or divergent lens, right? Now, keep it in mind for the lens, if the image. Now, remember for the mirror, right? The image will be real, right? When they are in the same side of the object, right? Am I right? For the mirror, if the image will be virtual if they are opposite side of the object. For the lens, this interpretation is exactly opposite, right? If the image is okay, I should write this, right? For the lens, it doesn't matter what type of lens, right? Image is real. If what? If in the opposite side of the object. Are you with me? Otherwise, it's virtual. Good? Hello?
Yes.
Yes.
Now the equation is the same, right? So you will write a 1 over F equal to 1 over dO plus 1 over DI. Now what I'm gonna do, I think it's time's up. I'm gonna stop right here. Okay, let me stop the recording.